So, good morning, all, and thank you for joining this webinar today. In this session, we are going to deep dive into a topic that is becoming increasingly important in the automotive industry, and that is how to successfully integrate machine learning into automotive SPICE version 4.0 framework. And before jumping to the webinar topic today, let's see high level at about ZooKoo Consulting. So ZooKoo Consulting, a company focused in engineering excellence for complex and autonomous systems. And here we have three main services areas that are important for automotive engineering. First is automotive cybersecurity. This service helps to the vehicles to be from cyber attacks or cyber threats. Automotive spice. This is the process to improve the software system and many other domains. All the processes there in those domains. Then automotive function safety. This is to ensure that electronic and software system are safe and effective. So ZooKoo offers expertise in various other SPICE models and extensions as well, which includes hardware SPICE, agile SPICE, mechanical SPICE, cybersecurity SPICE, and many more, like they are mentioned here. Next, here are some ZooKoo's core service offerings. So at ZooKoo, we have having expertise into 5 key areas. First is all about a team of certified assessors provides the various types of evaluations like audit in functional safety, cybersecurity, and gap analysis, formal assessments in automotive spice field. Then we help to bridge the gaps in we help or guide the teams toward the process improvement with the help of coaching. Then we help the organizations to define and document clear and compliant processes for the long-term success. At ZooKoo, we always share our thoughts to create a or follow integrated approach where we can define, document clear, compliant processes, and which are teams can integrate in multiple standards. And at the same time, at ZooKoo offers certified trainings for automotive spice, automotive cybersecurity, automotive functional safety, and these trainings are ZooKoo certified and Intex certified, both types. Some key achievements from ZooKoo. So ZooKoo is a member of Intex, and CEO of ZooKoo, he is the representative of Intex at India level, and many of the employees at ZooKoo, they are working, they are participating in multiple working groups at Intex again. ZooKoo is helping China and Korea Spice Network to grow, and ZooKoo Consulting is accredited training provider from VDA, QMC, and ECQ. Here are some numbers we have achieved in a few, multiple years in the past. So we are having 600 plus successfully trained, I would say, professionals, and some more numbers here in terms of Intex certified, competent level, PA level. Also, there are some employees at ZooKoo who are Volkswagen software quality improvement leader, squills we call them. This is a brief about me. I am Ankur Man. I'm an Intex certified principal assessor, along with some extensions like Agile Spice, Cybersecurity Spice, Hardware Spice, Machine Learning Spice. I'm also Volkswagen certified software quality improvement leader. And over the years, I have helped multiple teams, individuals to grow their processes and to meet their needs. Some points about this webinar. So all the participants shall be muted throughout the session and the camera will be turned on. And we will use MS Teams options like chats or Q&A sessions. options to collect the questions at the end of the webinar, and those questions will be answered at the end of the meetings or in future. So if time permits, we will try to answer here only, or we will answer them in future. Webinar will be recorded, and this recording and all the this PPT will be shared on this link. This is a ZooKoo website link, and under this webinar section, and the recorded section will be you can find that recording on our website or on YouTube. So with that, I think we can start our webinar topic today. So this is a high level overview of what all we are going to discuss today. First, we will talk about artificial intelligence and various other options within the AI. Then we will jump into MLE process group, that is machine learning engineering process group, and then supporting process. What all supporting process are there? So first one is all about artificial intelligence. Artificial intelligence or AI is the field. It is a vast field, and it is having any technique that allows machines to mimic human intelligence, from simple rule-based system to complex agents. Within this vast field of AI, we are having machine learning. This is a specific subset of AI that focus on using statistical method to enable machines to learn from the data without being explicitly coded. So this is the core of what we are going to, this is the core topic for the session today. And within that, we are having deep learning, which is a specialized subset of machine learning. It uses multi-layered neural networks to learn representations from the data. And this deep learning is what powers many of the most advanced AI applications we see today. So to summarize, every deep learning model is a machine learning model, and every machine model is a form of artificial intelligence. So next is about machine learning. In machine learning, as we can see here in the right side, we are having a flow. At its core, we are having a data, and this data is going to be fed into this algorithm, and this algorithm is going to run or it will identify the patterns or the relationships among that data, and this algorithms is job to find the patterns, correlations and rules within that data. Based on what it learns here, the algorithms creates a model, and this model is the brain of this machine learning, and that has learned something in the training period, and whether and the output or the task of this model is to take an input and give us some output, so based on whatever he has learned here. So once the model is ready, we can give any unseen new data to this model, and it will give you an output. In machine learning, we are having different types of techniques how the machine learning can learn. First technique is supervised, where, as the name is telling you, it is someone is viewing this particular technique. So the key attribute here is the label data. So everything, we will train the model with input and output both. Input we are referring as an X, and output we are referring as Y. So this learning algorithm will learn how to map the X to Y. Once it has been trained on this data, now we can give some unseen data as an X, and it will give you an output as Y. So if we take an example here, we train a model with thousands of images from cats and dogs, and we have labeled those pictures like all the pictures are saying that I am a cat or dog. So the model then learns to predict the correct label for a new unseen image. Next type of learning is unsupervised learning. So as the name is telling you, no one is going to help the model here. We will just feed the X. We don't have any Y here. So here the input data is unlabeled, and we only provide the algorithm with the data X. And the algorithm will find the patterns within the data by its own. And then it is going to club them in different groups. Then the last technique is reinforcement learning. This is which is different from other two. So in this technique, instead of giving a static data set like an agent here, this dog, uh, this agent is going to learn by interacting with the environment. The agent performs some actions and it will either receive a reward or a penalty. And the goal of this agent is to maximize this aggregated reward. So this is how actually the complete AI works. They will learn something based on some techniques. Three techniques we have here, we are having here. And based on that, it's going to learn something and then it will perform the action on unseen data. So that was about AI. Now we need to jump into MLE process group, which is a framework or V model cycle defined in automotive SPICE for version 4.0. This is a high level overview of this MLE process group. As we can see here, this is a new path that runs in parallel with the older software processes V model cycle. So it starts from SW1 and SW2. It will take some input from SW1 and SW2. So software requirements and software architecture elements will be taken as an input in MLE1 process, which is ML machine learning requirement here. So MLE1 process, it will take the software requirements and elements of here, and it will refine them into a detailed machine learning requirements, which includes ML data requirements as well. And that ML data requirements will be fed as a output to SUP11 process, which is ML data management. And this ML data management, after processing that data, it will give some output to MLE3 and MLE4 process. Once we are having structured requirement from this process, those requirements will be taken as an input by machine this second process, which is MLE2. Based on those requirements, we define the when the output of this process will come, and this includes the details of the model itself. So like number of layers in that model, a number of hyperparameters. So it is an important step that lays out the blueprint of this ML component. So in machine learning model, we refer them as an ML component. Then those ML components will be taken as an input by this process, which is MLE3. Here, this model will be trained with the help of data coming from SOAP11 process, because SOAP11 is, as we have already discussed, that is the process which is managing the data. So here we will use that data to train and optimize the model according to the architecture we have defined in MLE2. And this is where the model will learn something. And the output of this MLE3 process, which is a trained model, it will be taken as an input by upcoming process. And here we are going to verify that whatever the model we have choose, that whether that model is behaving correct or not. So along again the data coming from SOAP11 process, and we will verify the model here. So as we have seen that this SOAP11 process, this is the very important factor here, and data is the fuel across whole this picture. And ASPICE 4.0, it has find out that it is an important area. That's why we are having a separate process for that. So this process will ensure that continuous managed data is being shared among all the parties or all the processes who is going to need them. After this, we are having one outcome output link to SW5 process. So once that ML model is verified in this process, that ML model or component will be integrated among the bigger or broader software component system with the help of SW5 process. Also, we can see a loop coming back from this process MLE4 to MLE1. That's because we this is important because this is how the trained and tested model is integrated back in SW5. But at the same time, this MLE flow is not a linear flow. It is sometimes or many a times we have to come back and forward to readjust the requirements or readjust the components or different items within that ML architecture. So that's why we have to keep this. This is an iterative approach. It's not sequential in one go. Next is some common practices which are present in automotive SPICE, and same is present in MLE process group as well. And one of the common practices, you need to have a bidirectional linking among all the artifacts across the processes. So if we take an input for this process, MLE1, so we will take input from software requirements. So and that ML requirements, which are defined on top of software requirements, those can be fed as an output to MLE2 process to create ML component. And this is important in with the help of multiple ways. So here we are having 3 points. Like if we are having this bidirectional linking, it will ensure that our lower level ML requirements align perfectly with the higher level software requirements. At the same time, if a software requirements change, we can quickly and easily find out which ML requirements are affected because of those changes. And at the same time, it will allow us to prove that every single requirement has been addressed and verified, which will give you a concrete proof that it has been compliance with the standards. So in short, this bidirectional linking is the backbone of this process control, and it is how we ensure that our complex ML component or activities are fully aligned, and we are able to verify them across the V model cycle. Very next common practice is again, whatever you have done till now, you have to share all those things with all the parties. So after all the hard work in MLE1, MLE2 processes, now we have to agree upon all the requirements, all the results coming from those processes with all the parties we are having within the team. And here again, we are having two aspects. One is how you will share it. So methods to share the things. So this is not just about sending one email one time only. It is mainly it is about holding meetings time to time. So I mean, it should not be so frequent that you are spending so much time here only, but these meetings should be it should be occurring very frequently. But the topic or main point for these meetings are to formally review and agreed upon the work done. And at the same time, we have to document the things. So we have to define some templates or something so that we can document whatever has been agreed on. So these meetings are where we review the things and formally agree on the final outcomes. And this agreement is what gives the team the green light to start any other process after the MLE1 or 2. So with this, we have come to the first process, MLE1, and this is about ML requirements, which are here we are going to refine the software requirements we have taken as an input. So the purpose of this process is to take the general software requirements and refine them into a specific set of ML requirements. And this is where we define the ML component, what needs to be done. And it has some outcomes that is expected from this process. So first of all, we need to find out or specify the ML requirements along with the very important ML data requirements. And this is the first process, and here only we'll start talking about the data. ML data requirement is very important here. After this, we will structure the requirements. This is again an important step for project management and planning. Then the requirements, we have to evaluate them for whether those requirements are correct, whether those we can verify them or not. After this, we need to find out the impact of these requirements on the ML operating environment. Operating environment as in where this ML model is going to be deployed on. So some hardware, software, anything surrounding this particular ML component that will fall under ML operating environment. And as we have already discussed some common practices, we have to set up a bidirectional linking between ML requirements and software requirements. And whatever ML requirements we have agreed upon, we have to share it with all the affected parties. And the flow is showing the same thing. We'll take some input as software requirements. This we will execute one iteration of this process, and we will give some output that is functional and non-functional ML requirements, ML data requirements, and MLE 2, 3, and 4. Those will take these in ML functional and non-functional requirements as an input, and SOAP 11 ML data management will take the ML data requirements. In automotive SPICE version 4.0, we are having base practices. If you want to implement or achieve those outcomes defined in that process, these base practices will help you. And these are very much present in the PAM itself. So we can skip these BPs, but these are more like what we have already, talked about in that process. One more BP, base practice for this process. Now let's move on to some practical hands-on, how we can implement this process. So we are having we have to structure the process or all the ML requirements. So this simply having a list of requirements is not just enough. We need to make them manageable and usable for the project team. And this is done through two main activities. First is we have to structure the requirements, and then we have to set the priorities of each requirement, because not all the requirements are created equally. So we can define some priority for safety related requirements as high. And if we are having some performance related requirements, we can set them as medium type of settings. So, we don't have to have all the ML requirements, raw ML requirements. We have to structure them. That's first point in MLE1 process. Next is about you need to evaluate those ML requirements in terms of three factors. You can have more, but these are very key areas. First one is ensure we have to whether those ML requirements are correct or not. So whether we need to validate that our requirements are realistic and align with the industry standards. And is it either too low or completely unfeasible? That the question we need to answer. And these steps help you manage the stakeholder expectation, so that we will be ensuring our goals. Second key point here is to evaluate the feasibility. So we need to answer here, like, can we achieve the requirement with the current state of ML technologies, available resources, or can the model, if you are having a non-functional requirement that you need to perform this requirement within 100 milliseconds. So are we able to do this? So, and this requires a deep technical understanding for which you might need to perform some POCs. At the same time, we need to confirm that whether those ML requirements are verifiable or not. And this is a fundamental principle in automotive SPICE. Every requirement must be verifiable. And if a requirement is a vague, you cannot prove that the final product meets it. So this practice ensures that we can provide all the evidence for verification later in the process. And this analysis, it will support the key project management activities like project feasibility and estimations. It ensures that our ML model is based on the reality, not just as a wish list. Next practice is about ML operating environment. Again, some three areas here. So anything surrounding that ML component is will fall under ML operating environment. And we have to we are here actually we are asking, what does an environment need to look like to run this model effectively? And first of all, we have to assess the interfaces. So we need to understand the interfaces between our model component and the rest of the software system. Like for example, like how will the model receive the data from vehicle sensors, cameras, any other source of data, and how the output of this model will be passed to any other software components, like the complete vehicle control system. Then we have to find out all the infrastructure needs. So as we have seen that deep learning or machine learning, it can be very demanding. And for that, we have to find out whether we do have all the infrastructure like power, memory, and in many cases, might need to have some, separate hardware for those ML requirements or model. So, and this is specifically important for safety critical systems. Last one is impact on operating environment. So this is a broader uh, evaluation we have to do, where we will look at the complete system level changes things here. So for example, we need to have huge data sets for training purpose, but for that we to have a data storage. Also, we need to evaluate the network bandwidth. So because we are going to transmit the data here and there between multiple items within the component. So ML operating environment is the full infrastructure needed for both the training and the deployment of the model. And this practice will ensure that we plan for both the environments from very first step, so that we don't have any new findings in the future. With this, we have come to the very next process, MLE2. So if MLE1 was about what to do, MLE2 process is about how to do. So the purpose of this process is to establish a detailed ML component architecture, which is consistent with the ML requirements defined in MLE1 process. And the outcome of this process will be given, to the training process and the deployment model. And some outcomes which are expected from this process are like, we have to first and foremost, we have to have a ML architecture that is developed, and this is going to be a blueprint for the entire model. And then we have to find out all the hyperparameters ranges and initial values, and these are the configuration of our model that will be tuned during the MLE3 process. Then architecture elements themselves are formally evaluated based on some rules or rule something here. So we need to define those rules first, and then we have to evaluate those ML architecture elements. Then we are having interfaces. So we need to define the interfaces for all the architecture items there, eh, to ensure that they can communicate with each other and with the rest of the software system. At the same time, we have to set the resource consumption objectives, so that which is important for planning and optimizing the hardware where this ML model is going to be deployed with. And like we have seen in MLE1, we have to set up a bidirectional linking between ML architecture elements and ML requirements, and agreed upon outcome of this process has to be shared with all the parties. And the same flow is mentioned in this flow here. Like any other process, we are having some base practices here for MLE2 as well. So if you follow these base practices, you will be able to achieve those outcomes for this process. We'll skip these again because these are very well in PAM itself. So what is a machine learning architecture itself? So this is, as we have already talked about, it's a blueprint for our ML component, which is a document that specify all the sub components within that ML component. So if it follow these 5 areas, then we will be able to define a good ML architecture. First point is about data. So we must define the format, the size, how the data used to train the model. And this will include the documenting any data pre-processing steps, such, any data profiling. So those sorts of things we'll need to define here. Then the model itself. So this is the core of this outcome. We define the specific machine learning algorithm to be used, the model structure, and the hyperparameters that will be tuned during the MLE3 process. So we don't have to go in very much detail here, like to up to the individual, circle or very small item there, but a holistic view of complete, component we have to create. Then we are having training environment, where we need to define the hardware, software, frameworks, everything. Then the deployment, where the ML component is going to be deployed. That section is important here in the real world system. So we must define all the frameworks, where the model is going to be run with. So the model used for deployment might be different from the one which is going to be used for training. Oftenly, it is more optimized and smaller version. So those all things we have to think here. Last is uh, evaluations. So finally, the architecture what we have defined till now, we have to evaluate them, and for that we can define some metrics or the methods, and this include the some rules that will be used to ensure that model meets its requirements. So we also define the processes for model improvement. So it's not just one time, how we can support the model created in future as well. So those sort of maintenance activities or any information that we also need to define here. So by addressing all these 5 areas, the ML architecture provides a complete guide for the complete team. Now we have to talk about some relationship between parameter and hyperparameter. So hyperparameters are the knobs we can turn or tune to machine to check whether the machine is behaving fine or not. And with that, we are having model itself. So number of layers, activations, functions, and many other things. So combinedly, model design and hyperparameters, it will give you the model parameters. So model parameters are, I mean, these are not set by us or data scientists. These are set by themselves by the algorithm. So it will learn with the help of train data or hyperparameters values, and it will adjust those things by itself. So the purpose of this practice is to formally define and document the initial values and the possible ranges of these hyperparameters. And this will give you the foundation for the training and optimization that will happen in MLE3 process, which will ensure that our search for the best model is it's in, we are going through a process. We are not doing, something which is very, which is not useful. Along with that, we need to define some interfaces. So there are two kind of interfaces here. First one is internal. Internal interfaces are usually those which are uh, I mean ensure that internal interfaces will ensure that different parts of ML pipeline like such data pre-processing, the model itself, and the post-processing, they work seamlessly. Because if I mean we have trained the model and now it's going to give you some output, it's not like the ML model will give you some raw data which is not which is not easy to understand by human. So we need to transmit or transfer those data, raw data, into some meaningful information, and that we can present on the UI something there. So internal and then external interfaces are there which will help you like where our ML model connects with the vehicle's hardware or other software system. So to enable the real world function. So if you want, the model needs to understand the everything present, beyond that ML component itself, so that it can give some hint or some signals to any other component as well. So these both type of interfaces we have to define. With this, we have come to very next process, which is MLE3 process, and this is where we will optimize the ML model to meet the defined ML requirements. And again, it helps, it is also have some outcomes to be achieved. First of all, we need to specify an ML training and validation approach. Then we have to create the data set for ML training and validation. We had to optimize the ML model, including the hyperparameter values. We have to set up the linking, bidirectional linking between the ML training data, ML and ML data requirements. And at last, we have to summarize and share all the optimization outcomes and the trained model. Both the things we have to share as an output. So we'll take MLE2 process outcome as an input here, and ML data, which is coming from SOP11. We will iterate this complete process, and we will come up with a trained model, which has been trained on a data. And this trained model will be given as an input to MLE4 process, where this trained model will be verified against some new data, unseen data. Again, some best practices for this process. These best practices will help you to achieve a MLE3 process. We'll skip them again. With this, we are having a MLE4 process, which is very much similar to training, but now we are having different set of data. It's not a training or any other data. So specific data we are having to verify the ML model. So the purpose of this process is to ensure that both the trained and the deployed machine learning models comply with the defined ML requirements. So it will serve as a important quality gate before the model is released. For that, we have to define a testing approach. We have to create a data set, unseen or new data for the trained model. Then we have to define some test cases that are specified to verify compliance with the ML requirements. Then we have to define the ML model is formally tested using those cases, but we have defined just. And after this, some common practices like we have to set up the bidirectional linking between the ML requirements and the test cases and their outcomes. And at last, we will summarize the results and we will share all those things with all the parties. So as we seen in the that process overview grip picture, this process will give you a verified model which will be taken as an input by SW5, where this ML component will be integrated, in a broader software system. So that's how this complete process works. It will take a trained model from MLE3. It will take ML data and it will iterate it and it will give you a verified ML model. Some best practices for this process. These are present in PAM. We can skip them again. Now, this particular picture will give you a high level visual of entire training and how you will verify the pipeline. And this both the things are very much heart of MLE process group. This is where we bring our model, component in life with the help of data. So the process starts with the raw data here, and this raw data is, we will gather all, from multiple sources. And very much first step after this is feature engineering, where we will select and transform this data into a format which is suitable for our model. And again, we are having three kind of data, which we have already talked about: training data, validation data, and the data with the help of which we will verify the model. So the training data is the longest portion of this complete data, because this is that this data is the one which will help the model to learn patterns and every other thing. So it is what the model will see multiple times, because it's being going to be trained in multiple times here. So we are having this loop. So we will create the models, and with the help of training data, we will train them. And then once a particular model is, we find out that this combination of hyperparameter something, this is working well, then that model will be verified with the help of validation data. And once we find that a particular combination of hyperparameter values, those are working very well, then that particular model will be given as an input to the MLE4 process, where we will verify that model with the help of new unseen data. And then we will compare that whether we are getting the outcome as expected or not. So as we have talked about, we are having a whole data, and this within out of this data, we will separate them in three different set: training data, validation data, and the data with the help of which we will verify it. This picture is again showing the same thing. We will train the model. We will verify the model with the different set. And once we have a very optimal, model which is which is validated with the help of validation set, then we will give that model to verify with the unseen data. And then after we will compare it. Now, this is, as we have talked about in MLE3 and 4 process, we have to define that approach, how we will perform these processes. So, and documentation, something we will create, which will highlight some approaches for hyper parameter tuning, like how the approaches, what all the techniques are there, how with the help of which you can tune your optimizations of the model. Very famous technique is k-fold validations, where we actually we will divide our data set into multiple folds, and we will train the ML model in these with the help of these folds here. Then we will define the training environment, like all the software, hardware, or GPUs or supercomputer computer that is going to be, deploy with this. I mean, this ML component is going to be deployed with. Entry and exit criteria. This is a common principle practice in ASPICE framework. So here also we need to define when we can start ML model training on these or ML 3 or 4 processes, and when we can assume that these processes are done. So those rules or entry or exit criteria we have to define. And if required, some actions to organize the data and training environment. So this will involve all the steps needed to set up the training run. So those also we can define here. So this all together approach will help you. Which will help you that we are doing something which is not very new something, but it's an experiment, but a controlled and well-defined activities we are doing here. If we are following this approach to define a complete strategy. Then hyperparameter tuning, as we have already talked about, there are multiple techniques with the help of which we can tune our hyperparameter settings. First technique is about to try all the combinations, and second technique is we will not try all the combination, but we will pick any of those at any time without any pattern. But again, we are not in both the techniques, we are not seeing any past behavior. That's why this new technique will help you, where you will see the past behavior, past outcome of a old hyperparameter combination, and based on that outcome, you will pick any other combination in future. So like that, we are having more techniques like this hyperband, fifth one. In hyperband, this is very efficient and modern method. It will give you the resources to multiple hyperparameter settings, so that you can eliminate those combination which are not behaving fine. So it is a great fit, but it will give you the finding as soon as possible. But it is having a I mean, if you are having a budget that is not something which you can go for, that you can use this particular technique. So choosing the right method for hyperparameter tuning is a key part for defining our training approach, and it is very important for building a high quality model. Now the last one, supporting process, and we are having one process here, that is SOP 11, and the purpose of this process is to define and align ML data with ML data requirements, which is to maintain the integrity and quality of the ML data, so that it can make it available to all the affected parties. Some outcomes for this process, that we have to set up an ML data management system, which is including an ML data cycle. Then we have to define a data quality approach, including the ML data quality criteria. And we have to collect the ML data, which is going to be processed for ML data requirements. So and we need to take care here that whether that ML data is synced or linked to the ML data requirements or not. Then ML data is verified against the defined ML data quality rules here, and as we have updated as needed. ML data is agreed upon, and it will be shared with all the parties we are having within the team. So the SOP 11 process is the backbone of this ASPICE for ML framework. It will ensure that most important asset like data is managed, verified, and made ready for the use in ML model cycle. So ML data requirements coming from MLE1 process will be taken as an input here. We will iterate or execute the complete SOP 11 process, and it will give you the complete ML data, which will be used in MLE3 and 4 process. Next is this is a comprehensive overview of ML data cycle, where we are mapping the status of the data to the corresponding software and data processes. So we are having three steps here: planning, build, and operator. We are having all the processes, MLE 1, 2, 3, and 4. And from one side to this side, we are going to perform some action on the data. So we will have all the data gathered from multiple sources first. So here the data is labeled, or the status of that data is raw, we are mentioning here. Then we will perform some I would say some action on those data to clean it. If they are we are that data is missing some values, then we will fill those values. So all those sort of activities we will do, and that's why the data is marked as cleaned here. Then we will label those data with like X and Y, the technique we have already seen. Those labeling we will do, and that's why the data will be referred as labeled here. And after this label data will be given as an input to MLE3 process, where this model will learn something. And after this process, we will have a trained model. And after this, we will be having a complete new unseen data that will be used by MLE4 process, so that we can verify the whatever ML model we are having, that is behaving fine or not. So this is the complete overview of the complete status of data. At last, we are having the concept of data. We have to gather all the data, but we are having multiple questions here, like what all to be collected, and from what all the methods are there, and where actually we are going to store those data. So all those sort of questions we have to answer, and there are some techniques for all those questions. So like what to collect, we can collect data from website. We can collect data from with the help of web scraping. Web scraping is something where from the website itself you will fetch some data. And what all the options are there to store the data. So we are having some databases, some data warehouse, some data lake. So these complete overview is there to manage the data. So data management system has to answer or implement all these questions we are having. So till now, we have talked about a comprehensive look at the machine learning engineering process group, which is introduced in Automotive SPICE 4.0. And this is a significant update that address the unique challenges of creating and we have to create AI systems in a structured and quality controlled environment. And the purpose of this PPT, what we have talked about today, is to give you a clear or a practical understanding of the ML cycle from requirements, when from the requirements, and when actually you will create that ML component, and then you will train it, and then you will verify that model, and how it maps to the ASPICE processes, which we already know. So this is this we have lay down the foundation for building the robust and compliant machine learning processes within your team. So with this, yeah, we have completed this topic for today. And here are some trainings, upcoming trainings we are having at ZooKoo. If anyone's interested in PE, PA, or any specific training, agile, spice training, machine learning training, then they can enroll themselves by going through website. So, and this QR code as well there if you want to go for those trainings.